Vaughn from the National Science Foundation in our program for Small Business Innovation Research Grants. Welcome to the 8th Annual EdGames Expo and to this evening's masterclass session, where an education technology developer will provide educators an example on how to implement a hands-on engineering design challenge with middle school students in a remote learning environment. The Next Generation Science Standards, or NGSS, is the country's most widely used approach to teaching science, and it places a large emphasis on students doing authentic investigations as real scientists and engineers would do. The goal is to help equip our students with the skills for future careers or further education in STEM. However, authentic science labs can be very difficult to implement in ideal conditions, let alone in hybrid and remote learning situations. Pocket Lab, with grant support from both the NSF and the Department of Education, has developed tools to make science more accessible and engaging for students in any learning environment. Today's masterclass features an engineering and physical science challenge where students had 48 hours to develop and test a cold storage device for shipping vaccines. After today's masterclass, please stay tuned for an engaging question and answer period between the developer and a group of science educators. Now off to Clifton at Pocket Lab.
Hi, I'm Clifton Roosboom, the founder of Pocket Lab, a wireless technology system for doing hands-on science learning that we use with over 300,000 students in 62 countries. In this video for the EdGames Expo, we will talk about our engineering design challenge, where middle school students designed a vaccine cold storage device over a 48-hour period, iterating on their engineering design multiple times. Students use Pocket Lab Thermo, our wireless temperature sensor, to collect data from their device, and Pocket Lab Notebook, our online cloud software, to communicate their findings with both their peers and the teaching team. The videos you will see are a collection of our Zoom meetings with the students and video clips that they use to document their engineering design process. The development of the Pocket Lab technology has been funded by Small Business Innovation Research grants from both the Department of Education and the National Science Foundation. Without that funding, none of this would be possible. So we'll begin by explaining more about Pocket Lab and our journey so far. What science questions have you always wondered about? Why does lightning strike? What causes ocean tides? Why do you get butterflies on a roller coaster? The joy of science is exploring the questions that you've always wondered and exploring the world around you. We believe anyone can be a scientist, and science doesn't just happen in the lab. If you had a device to help you explore science, what questions would you ask? Pocket Lab is a wireless sensor that enables you to gather data from the world around you. Pocket Lab connects with a single button to a computer, tablet, or phone and displays the data in real time. In seconds, you can do experiments that were never before possible. Pocket Lab is intuitive and fun and ready for anything. In 2015, we launched the first Pocket Lab with awesome support from users all over the world. The Pocket Lab app can record video and sync sensor data to create amazing science videos. The app integrates with the cloud for mapping features. You can learn coding through Scratch or with Lego robots. With an open API, the Pocket Lab will allow users to create custom apps.
Being able to take a Nerf ball, cut it in half, slap the Pocket Lab inside of it, rubber band it together, and then kick it and videotape it was extremely powerful.
I give them Pocket Labs. I say, I want you to tell me something new and exciting, something that you can measure with Pocket Labs.
Usually with earthquakes, we use accelerometers to kind of look about how stresses and strains are built up and how they release over time.
I needed to know what the displacement was and what the forces were on this particular part of the machine while it was running.
Explore, engage, and discover the world around you with Pocket Lab Voyager and Pocket Lab Weather. Please back our campaign and start exploring. Hold up your your device and keep your smiling face in the camera in the shot as well. Love them. It's great. Very impressive. Thank you guys.
My name is Avani. I live in Los Gatos, California. I tested how cold the vial filled with water that is refrigerated for 30 minutes can stay cold by using inexpensive, simple, and different methods of insulation. This will help us to develop ways to keep vaccines cold at low temperatures easily. I learned that styrofoam, bubble wrap, and plastic are great insulators. I also learned how to use the Pocket Lab thermosensor, and it is pretty cool. The most important materials that I used in my final design was styrofoam and bubble wrap. These materials have small air bubbles trapped in them, which doesn't allow heat energy to flow through them. The starting temperature of the device of my test sample was 7.01 degrees Celsius, and the final temperature was 9.03 degrees Celsius. The total change after 2 hours of testing was 2.03 degrees Celsius.
For the challenge, my idea was to use different layers of insulation using like 2 different materials. I decided that I would have the better insulator as the outer layer and the one that wasn't as good as the inner layer. I was looking for different materials. The 2 materials I tested were styrofoam and bubble wrap. I tested both materials at the same time, and I found that the styrofoam was a better insulator than the bubble wrap. The lowest temperature the styrofoam got to was 16.7 degrees, while the lowest the bubble wrap got was 17.6 degrees. The vial and the styrofoam heated up a lot, but heated up slower than the vial and the bubble wrap. Using the information, I decided to have the bubble wrap as the inner layer and the styrofoam as the outer layer. I did the final test, and the lowest temperature showed up as 11.81 degrees, which is a lot lower than the first test. The final temperature was 17.47 degrees after the full 2 hours, having a total change of 5.66 degrees Celsius. And based on the testing, the double insulation allowed it to reach a lower temperature than having just 1 layer, and it was about 5 degrees lower.
Hi everyone, my name is Alyssa Clausen and I live in Los Gatos, California. Just wanted to say, if you're nervous, you're not the only one because I'm super nervous too, and yeah. In my experiment, I tested how well my vaccine cold storage container insulated the cold air for the cold pack. I learned that R value is how well the material resists heat flow. I also learned a few materials that have a good R value, like cellulose and polyisocyanurate. My design is a cardboard box surrounded with cellulose fibers, and on the inside are layers of polyisocyanurate film. I tightly packed and cut every single piece of material so that there wouldn't be any place for air to escape, because I want to keep the cool air in the box. The most important materials that I used were polyisocyanurate, cardboard, and cellulose. Polyisocyanurate has an R value of 6 per inch, and cellulose has an R value of 3.5 per inch. I used the cardboard to hold everything in place. The temperature my vaccine cold storage container started at was 1.91 Celsius, and the final temperature was 8.5 Celsius. The total difference was 6.9 Celsius. That was for the first 2 hours. I recorded an extra hour because I just wanted to see how well my box insulated.
Hi, my name is Mateus Thompson. I live at Cheyenne Mountain, Colorado Springs in Colorado. I tested whether plastic wrap or bubble wrap would give me the seal that I need on my box to keep the temperature under 40 degrees Fahrenheit, which was my goal. After a few tests, it became very clear that plastic wrap wasn't the best solution to my problem because it had a starting temperature of 37 degrees Fahrenheit and an end temperature of 42 degrees Fahrenheit. And I wanted to keep it under 40 degrees. I then went back to the idea board and bubble wrap came up. I then switched out the plastic wrap for bubble wrap and started testing. The tests came out astoundingly positive, so I went back to bubble wrap instead. 37 degrees Fahrenheit to 31 degrees Fahrenheit. Each of the previous tests were only 30 minutes long, and the final tests were 2 hours. After the 2 hours concluded, I saw that I made the right choice of using bubble wrap to surround my design, 37 degrees Fahrenheit to 33 degrees Fahrenheit, with a 4-degree change. My full design was a box that has aluminum foil on the surface area on the inside of the box. The purpose of the aluminum foil was to reflect any thermal heat, because aluminum foil doesn't absorb or transmit thermal radiation. Next, I measured the box's dimension to perfectly cut styrofoam that would surround the entire inside of the box. The purpose of styrofoam is to prevent any heat molecules from entering the box, because the styrofoam is so dense that it is hard for any airflow to occur. I then, for some more installation, put cotton balls in the middle of the box for 2 reasons. 1, to prevent the cold from escaping, and 2, because if this was really being transported around the world, the vaccine would need a soft cushion when it is being moved around. And of course, the bubble wrap was put around the box to get the airtight seal, and it helped a lot. And that's my design and why I chose the material that I did.
My name is Stuart Chen, and I live in Sunnyvale, California. So what I tested was, I took a cardboard box, and I put this thing that looks kind of like bubble wrap, but also looks like foil. It looks like this, so it's kind of like a mix between them. I put it inside, and so for the first test, I put the vials on the bottom, and then I put the cold pack directly on top. And for the second test, I actually hung the vials in the middle of the air from the temperature probes on the Pocket Lab, so that, and then I just put the cold pack on the bottom. So what I learned was that when the cold pack is directly on the vial, it is better. And so for the final design, I put an extra piece of this bubble wrap thing on the top, so that, because I noticed that during the test, cold air was kind of coming out through the top because it wasn't sealed very well. And so I think that helped.
If you could test it again, if you could make some more changes and improve your design, is there anything else you'd want to add?
Well, I would want to test it with and without the bubble wrap, and also other materials to see which one is best, because both of my tests had this bubble wrap in it, and so then I don't know what it's like without it. So I would definitely do a lot more tests to figure out what's the best way.
Awesome. Yeah, great idea.
Okay. Hi, my name is Heather Hansen, and I live in the Santa Cruz Mountains in California. And I did 4 trials. I did trial 1 and 2 on day 1, and 3 and 4 on day 2. And on day 1, I used a bag that has foil on the inside and bubble wrap on the outside. And this is day 2, and it's inside out. And this is day 1. This is right side out. And I used an insulator, foam beads for both of them. And trial 1, I tried to suck the air out using a straw, but I think that it wasn't successful because I didn't seal it correctly. And trial 2, I wrapped the vial in a cold pack, and then I put it inside a right side out bag and put foam beads in it, and I sealed it. And then and then trial 3, I had a bag that was inside out, and I also used foam beads, and then I wrapped it in foil and put it in the bag. And then trial 4, I just wrapped it in foil and I put it in the bag. And the most successful trial was trial 2, and the starting temperature was 6.9 degrees. And my final temperature was 14.2 degrees, and the total change was 7.3 degrees. And I learned that foam beads is a good insulator, and the most successful design was the trial 2 with the right side out bag and foam beads.
The first and second trial was more successful than the third and fourth trial.
The first trial had no beads, and it was from 5.96 to 15.06. And the second trial in the first day had beads, and it ranged from 6.97 to 14.21. So the first day and the second trial was the most successful.
So you're the first person that we've heard talk about. You said you try to suck the air out of your device. What was the thinking behind that?
Whenever I got something in the mail that had to be kept cold, and I noticed that it was sealed really tightly, so I got inspired by that, and I think that it would be more successful if I sealed it better. And I was going to try to use salt and ice, but I was worried it was going to contaminate the vial.
My name is Sophie Reitzma, and I'm in Los Gatos and in California. I tested whether the combination of foam and foil would keep the vial cold. Foil acts as a wall to keep out heat, and it keeps the cold in. Foam does a great job of keeping things cold because it will like poorly conduct heat, and if heat tries to get into the container, it will come at like a really slow rate, therefore making it really hard for it to heat up. And so we will put the cold pack here because cold goes down. Yeah. And so I have another polystyrene slab here, and I have wrapped it in foil to keep it cold and to seal everything in, so that's nice and stuck in there. And just close it up and tape the sides up, and there's my contraption.
Hi, my name is Etienne. I live in Los Gatos, California, and I didn't really have that much time to test it, but I managed to do one final test, luckily. And my design was based on the Zipop, where basically you put the vaccine and whatever insulation inside with the probe, and then you put it like this, and then I hot glued the top with the wire going through so it could record it, and then we put the milk carton upside down with a small hole in it, so a little bit of water could go on the sides, and the water evaporated. The water evaporates to take some of the heat away with it. And yeah, we didn't use one of the cold packs, like the chemical cold packs. We just used some ice. The water tank, which is going to drop little drops on the top of the bowl to make sure that it runs down, and then the water will evaporate, taking small amounts of heat with it.
Number one project in the competition is going to go to Alyssa Clausen. Yeah, so you had, we think it's the best project overall. We think you did a really amazing job explaining all your thought process in the video. You really went above and beyond into research on, insulators and everything, and we were super impressed with all your work, all your hard work designing and cutting stuff so it fit together perfectly. You really did a great job, so thank you so much.
Thank you so much.
Yeah, I think just overall, it went great. They really picked up how to use the Pocket Labs really quickly. I didn't get a lot of questions about how to use stuff. They just learned it from just our little workshop we did at the beginning. I was really impressed with their creativity. A lot of them started brainstorming ideas before the competition even began, or they asked me questions like, "Oh, can I use batteries, or can I hook this up to a fan to keep things cooler?" And really just throwing out all these things that we never even thought of. So super cool.
Yeah, that's fantastic.
Yeah, and I was just really impressed by their ingenuity, and especially in the remote learning environment, being able to kind of independently think of these really creative solutions to a problem. And I know it's a lot more of a difficult setting, not being in class, not being able to collaborate with their neighbors in a lab group right next to each other. But so having that being remote, but then kind of thinking through those problems independently and coming up with really interesting and creative solutions that I would have never thought of. I thought was really impressive.
Yeah, it was fun. There were a couple students that got to do it as a team with their sibling.
Right. Yeah.
There's not a whole lot of lab group work otherwise going on, so that was fun.
Yeah.
Yeah, it was really cool to see. I remember one of the videos, like one of the students, their little sister helped them like pop the cold pack, and then hearing both of their reactions when it started getting cold was really cool. We're both so excited.
Yeah. Well, let's do it again sometime.
Yeah, definitely.
Yeah.
Hopefully in person the next time we run this.
Yeah.
Hopefully.
Thanks, Pocket Lab and Clifton, for introducing us to your challenge and showing us how it works. Now we're going to actually take to some educators from around the country and see if they have any questions about what you guys did over at Pocket Lab with this very timely challenge. All right, who has a question from our group? Eric, can you tell us where you're from and also your question?
Thank you. My name is Eric Walters. I'm from Marymount School of New York in New York City. First of all, what a really great activity. When I watched it, I was like, I cannot wait to do this with my students. Also a longtime user of Pocket Lab. So one thing I noticed with the students had access to a lot of materials in their homes. So how do you envision developing a project like this for students that are in under-resourced schools or remote learners?
It's a really good question, Eric. And, you can get more regular outcomes if everybody has, the same starting point. But then that's also a limit to creativity. And, in ideal scenarios, when people have the capabilities to go off and use whatever is available, that's how we like to approach it. But our team in all of our lesson development, that's something that is especially hard for middle school and lower grades, where even in the classroom, whatever equipment that you might have, we never know. Do you have beakers? Do you not have beakers? Do you have Bunsen burners? Do you not have Bunsen burners? And some things just require equipment. Like if you're going to do a reaction and you need to heat up a substance, you got to heat it up somehow. So I don't know we try to provide starting points, but how do you see resources availability in across schools or in your experience, Eric? How do you see?
I think it's certainly been a challenge this year, and specifically, I was asking, how do you get the Pocket Labs in the hands of the students?
Well, that's a tougher question. We are hands-on. We have this is what students were using was our temperature probe, and there's a real cost to this and to shipping it to students that is unavoidable and isn't scalable like software is. I don't know. We haven't solved that problem. We try to make it as low cost as possible as a starting point, but it's still $39, which for a kit that you send home with students, that's not doable for most places. If the Gates Foundation wants to fund some hands-on science kits to Marymount or wherever, we are pursuing things like that. But foundations, it's a long process.
And let me just jump in. Clifton is a phase 2 recipient of a National Science Foundation grant, as well as a Department of Ed. And one of the reasons we give these grants is because, at least with the NSF, there's a technical challenge to be met and passed. And so phase 1 was about that. Phase 2 is about the scaling, which also is technically challenging, and then marketing and getting the word out. So Eric and everyone listening, this is all part of getting that word out. We would love to get these in the hands of everyone or anyone who needs or wants them. and all ideas I'm sure Clifton is would be open to.
Yeah, all ears.
All ears. Thank you so much for that question, Eric.
And I can add one other. I'm Robbie from the Pocket Lab team. I can also add one thing specifically about that activity and what Eric mentioned about students being at home. You know, there are in some of our activities lately that we've been writing ever since the pandemic and with students at home. There are elements that we try to write in if a student may not have a Pocket Lab. So students likely don't have Pocket Lab sensors at home. The teacher may have them in, at their house when they're doing remote learning. So we try to include example data for certain activities, or we have instructions for the teacher maybe to do a demo of the lab and then think about what are some ways that the students could then do a similar activity at home. And so for this, if they have meat thermometers or other like thermometers at home, maybe whether it's one that you use for health or meat thermometer, there is ways that you could do certain elements of the activity with that. Obviously, it's going to be much richer with a Pocket Lab because you get that data over a long period of time. But there are some alternative ways you could do a similar activity with maybe thermometers you might have in the house. And then with Notebook, there are ways to add data manually with data tables. Or even you can even put data into a CSV file and upload it and get like a graph, or you can add scatter plots of data, things like that. So there are some ways you could do it that way. If you're kind of in a remote setting, you can't send all your students a Pocket Lab sensor, obviously.
Thanks, Robbie, for that. We have a couple other questions here. Christine, can you ask Clifton a question about the program and unmute? Excellent.
Hi, my name is Christine Gertain, and I teach a 3-year science research class in Toms River, New Jersey, but I often work with younger students during camps. And so I was wondering whether there were going to be camp options for this as well, besides just approaching it from a classroom level and doing it with teachers. And will you be offering asynchronous and synchronous learning for students? So if there's a student that couldn't attend the camp or do something I was doing for a STEM camp over the summer while we were live or in person, would there be a way or something that's videotaped, similar to when we were watching the masterclass with all the kids coming in, but they were live, that they'd be able to follow and then explore and then maybe add their thoughts or questions to afterwards? And would there be someone to give them feedback, or would that be on the camp teacher? How would that run?
Yeah, that's a really good question, and an interesting idea that we've been thinking of, for a while since the shutdown started, and more for in-person teaching, but the spin with the science camps is also interesting. Yeah, we're exploring, what is the right way to deliver this content, and it's always less than what we want it to be, because we want kids tangibly touching things and building things. And if it's a summer camp, launching an air rocket and measuring, like strapping on a Pocket Lab, measuring the altitude of that rocket, and then doing a calculation on their own. So there are easy ways for a teacher to collect that data, and then for students to analyze it and to answer questions through Notebook. It's just so much less fun, but that's the reality. But there is, we can deliver the boring part, the data analysis and the writing part pretty easily. The fun of building, we're trying to find ways that's scalable, and an inherently not scalable kind of activity.
Yeah, but you're doing a great job. And again, people talk to me that these grants are for commercialization purposes, getting in the hands of students. It really is challenging to choose the direct way, or all the ways you could do it, and narrowing it down as what do we have to do first. And I think, Clifton, you're doing a good job, but I think Christine has a fantastic idea there. So we should all be thinking about camps coming up this summer. All right, Sarah, next question for you. Thank you, Christine.
Hi there, my name's Sarah Kendrick. I teach in Madison, Wisconsin. And my question is, how do you walk students through the process of how to use the equipment, how to use the probes that they're using, as well as start working with the data and entering that? Is there a process that you use for that?
Yeah, and I'll answer briefly, then ask Robbie to step in. So Robbie leads our product development of Pocket Lab Notebook, and he was a classroom teacher for 6 years, so can speak more intelligently to it. I mean, what we found is, students are digital natives at this point, and they ramp up really quickly. It's actually like the teachers that require more training typically on how to deliver the content. But we spend a lot of time on ease of use design. So, these students, they're all 8th grade and lower, self-selecting and very smart, but they got it without any much intervention, about 15 minutes of training on a webinar that we kicked off the design challenge with.
Yeah, and one thing that we also do is we build in some of these tutorial what we call lab reports. In addition to the one kind of you saw, we have these tutorial ones that teachers can actually assign to the students, and videos pop up and it shows them how to turn their Pocket Lab on and connect and do some of these basic things. So there's actually some early activities that we kind of encourage users to do right away to make sure that they know how to connect and get started with that. And then we're always looking for, like Cliff said, we're always trying to figure out ways to make things more intuitive and easier to use. And then also adding, different tutorials and onboarding features and things like that. But yeah, we have a lot of those sort of trainings and video on-demand kind of videos that students or teachers can watch, and that kind of walks them through some of the basics. And that way, then the students always have access to that. So if they want to go back and watch a video again on how they connected, or how they're supposed to connect, or change the data rate or something like that, those are all there in their tutorial. So we try to make it like independent. The student can do it independently as well as get the training from a teacher.
And we have 2 AI projects we're working on, funded by the Department of Education and the National Science Foundation. So hopefully in a couple of years, there will be this AI helper like embedded into our app, helping a student guide them through these activities. But that's down the road.
And that is such a great thing, because teachers are overwhelmed. And as you said, the students are natives in this environment. And as much as we can assist both the student and especially the teacher on minimizing uptime or training, and that's great with all those on-demand videos for both the teachers and the students. So thank you. Okay, Kathleen, I think I see your hand up. You have a question for our team.
I do. My name is Kathleen Fredette, and I'm the Director of STEAM Initiatives with iLead Charter Schools. Love design challenges. It's really one of the things that I think our kids across K through 12 really went through this year. So happy about this. Here's my question. In what way do you see what you've developed and what you're developing supporting the effective or the ability for kids to maneuver performance assessments that we're required to administer and use? It's a beautiful skill. So that's my question. Performance assessments, connection to you guys.
That's a really good, cutting question. Assessments is certainly the next thing that we're trying to tackle. And how do you, in general, how do you assess science when it's so skill-based versus content knowledge-based? And we hope that eventually you can do that in Notebook, kind of stealth in the background, looking at how students are applying, SCP-4, like analyzing data, interpreting it, which, isn't something a standardized test or multiple choice questions, I think, can really get at. It needs to be more open-ended. So I would say it's something that we're very aware of and we're working on. I wouldn't say we definitely don't have the solution yet. how do you think about science assessments?
Nice job on turning that back around on a teacher. It's something, right, that we're all moving towards. I think, especially in science or in STEM, we have to find a way to help our facilitators develop performance assessments as they're moving through content. So I see what you're doing, and you give a kid an opportunity to have this experience with data, and then you create something over here that looks a lot like that, but they have to apply it in a new way. So yeah, the skills are being formed. So I think you guys are like poised for creating this. And then I think the more we do it together, then we can borrow. What did you do for third grade? What did you do for fourth grade? What did you do? And that's the power of, I think, what we found this year as educators.
Yeah, thank you.
What a very timely question. And assessments are always a challenge on all sides. We want to assess how we're doing, but it certainly is a challenge. So great question, great answer, and it sounds like it could be another 12-hour topic discussion that we're not going to have today. Let's move on. I think, Nicole, you had a question.
Yes, hello. So I'm Nicole True. I'm teaching middle school science at a school in LA, and I'm really grateful for this opportunity to learn about another very great resource, especially for virtual learning. But my question is, what are some common challenges that you have heard from middle school teachers trying to implement Pocket Lab during for virtual learning currently?
I think we're like a second, maybe third tier priority, to be honest, where like number one is getting your students to attend and like them figuring out email and Zoom and Google Classroom. And then it's like having a really good hands-on like science lesson. So, you know, if you're dealing with like social emotional learning, and you teachers, like your counselors, your like therapists, your educators, you're so many things. We're practical about it. Hands-on science hasn't been at the forefront of people's thinking over the last year. So I think it's those like more fundamental needs that are, that's the roadblock. Like, are those being met? And then, right, it's a resource thing. Do students have a Chromebook or a computer or an iPad, and do they have like a good internet access? If you don't have those things, we are an inherently digital solution, and we can't even get started if you don't have good internet access.
That was an excellent question. This year has certainly been a challenge, and of course, teachers wear so many hats, including teachers, but sometimes that's the third or fourth hat they've got. You're right, Clifton. There's a lot going on this year that we've all dealt with. Looking forward to getting into, as Christine just chatted, the hands-on exciting stuff is what gets the kids to come to school. So great answer, great question. Thank you very much, Nicole. I believe we have another question from
Teresa.
Teresa,
Hi.
what's your question?
My name is Teresa, and I am from the Saugus Union School District in Los Angeles County, and we are traditionally a very funding is very challenging for us. We don't qualify for a lot of special grants. And so my question kind of piggybacks on a lot of the other questions, in that you had talked about getting Pocket Labs into the hands of students obviously is a challenge because of cost. And as we're doing hybrid as well as strictly online, we have a mix going on in our district. Do you foresee not just videos about how to get it up and running, but demonstration videos for those classes that can't afford the actual equipment to get distributed to every student, but instead would have not just their classroom teacher demonstrating it, but an expert demonstrating it in the field?
Yeah, that's a great question. For all the activities that we're developing now, we're really focused on middle school physical science in our sort of development process right now. We have that, example data as, a preview for the teachers to know exactly how is this activity going to go. And then, it's kind of up to you whether you want to keep it in there first, and then before you send this to students, or you could take it out so that it's a mystery. But yeah, there's this pre-recorded data and videos of the experiment. So if it's like a reaction, that exact, mixing the chemicals in that reaction, and then the data that we could collect from that to preview to you. And then if in a remote setting, you can then push that on to students where they're doing the boring part of the data analysis and the writing up their findings. At least they have real experimental data to do it with.
Wait, they have to write up their findings?
Yeah, communication. That's like my biggest job is communication of science, and it's hard. The mixing of the chemicals is the more fun part, I think.
I think most of the students would agree with that. But communication is essential in every career you go into. So that was a great question as well. Really appreciate it. Clifton, do you have any final thoughts about how your team came up? Actually, my question, how did your team came up with this idea? I mean, this is something please share with us.
The original seed was that we wanted to give people a Swiss Army knife that let them go explore the world around them, where they, I don't know how, this motor works or why it's shaking. Like, is there something that I can stick on there that gives me insight into how it works? And the Swiss Army knife concept that it's small and portable and useful in many different situations for you to understand at a physical and engineering level what's happening. So that was the original seed. And my PhD research was in sensors for like smart city, Internet of Things types of applications. And that's how this started. In the last year of my PhD, was like, this should be easier. Shouldn't require a PhD to, collect this kind of data. And now here we are, 6 years later.
It's a long road, but it sounds like from the reactions you've got today from these educators, you have a lot more work to do for the next 6 years. And we really look forward to seeing where Pocket Lab goes from here. Thank you very much to the educators on our panel today for participating and giving us such great questions. And we look forward to seeing the exciting post-pandemic future.